I'd like to thank you, the organizer, thank the organizer again for having me here again. We're going to give a talk now about catalytic and asymptotic equivalence or entanglement. With the subtitle, whatever, can your bank help you to distill more entanglement? You can think of this as like a prequel to the talk yesterday. It's weird, but okay. And this is again joint work with C people. Varun is graduating, so they're hiring. No, and Alex who's here in the audience. All right, let's start. So let's run through standard entanglement theory because I would guess most of you are familiar with this. Entanglement, you have many parties, right? They can communicate classically, and they can do some local operations to their part of the system, right? And mathematically, it's an LCC, right? Separable states are free states. You can create these states for free. And whatever that is not separable is called entangled, and entanglement is useful for many things. Your favorite use case, whatever. But usually this entanglement is usable with, it's very specific, right? If you want to do teleportation, you need your system to be in a state. It has to be a well state. If there is some noise there, your teleportation is going to be noisy too. And real world entanglement sources do give noisy stuff, right? So how do we deal with this? Standard answer is, well, okay, deal with noises. Standard answer is that you take many copies. If your source is not just going to get one thing, you can press the button again, it's going to give you a bunch of things, right? And there's this thing, very old by now, 20 years old, that you can purify entanglement with distillation procedure. So you take many copies of noisy entangled states, you convert them into lesser number of pure entangled states. So far, so good. And the maximal rate at which you can do this procedure is called distillable entanglement formula. And if state is distillable, it's called distillable, but there also exists an entangled state that you cannot distill any singlets out of. They're called entangled states. So far, so good. Read you over. But you can sit back and like think to yourself, why do you limit yourself to those? Right? Because sure, it makes complete sense, but we live in a capitalist society, we have banks, we can borrow stuff. Does any of these results, the things that I told you before, really change if we can borrow time? There's a question. So this borrowing stuff, you can make it formal. Again, I guess also you have seen this, but I'm just going right through it. There's this thing called exact catalysis. So you have a catalyst state and you have your LOCC protocol so that you borrow the catalyst and then in the output you get the catalyst back again. And it's uncorrelated, you can use it no matter how many times you want. It's all good. I think this was introduced actually by Jonathan and Glenn, who's here. Very nice. So the question is, you know, something like this, how powerful is this transformations? Can you do more than just single shot usual LOPC without yeah, in particular, can you find two states so that with your LOCC you cannot do transformation, but with exact catalysis you can. Of course, the answer is 99 favor is that yes, it's possible. Right. So in 2005, Juan has a paper that connects this setting of exact catalysis with asymptotics. And the statement is, if you can transform psi into phi, I think it works for pure states, right? If you can transform pure state phi into psi into phi, many copies, for some n, then you can also do it catalytically with exact catalysis. And this might seem surprising because exact catalysis operates on a single copy level, right? You just have one copy of your state, you borrow something, and then you can do the transformation. Whereas this thing is many copy, right? It's asymptotics. So yeah, it's asymptotics. But of course, because I already gave the answer here, I already spoiled the answer. So why you can do this is essentially because you hide many copies of the input state and the output state. You do it in clever ways so that you can achieve asymptotics with single shot, with catalysis. But it's still like really interesting that actually catalysis kind of allows you to go from single shot kind of results to asymptotic end results. This is nice. I think with exact catalysis, we can actually even right now what kind of conditions is necessary and sufficient for two states to be inferred to be transformed one into another. But I mean, it's thanks. All right. What I want to do instead is like to relax a bit the definition of catalysis. Instead of exact catalysis, let's do correlative catalysis. Again, it's also in the slide yesterday. So in this definition of correlative catalysis, what we do is instead of having the output state exactly be sigma tensor to catalyst, the output tensor catalyst, we can allow some correlation between the system and catalyst, which is required that the state of the catalyst is exactly the same because we don't want to embezzle any resources and stuff. And we can also allow any error, but this error is just on the level of the system. You can make it more, I don't know, more restricted by, for example, requiring that the correlations between system and catalyst can be made arbitrarily small, but this, I would say this is kind of like the bigger set, right? And we'll show eventually later that this setting is related to asymptotics and also what can you do with distillation if you allow this kind of setting, but in addition to others. Right. So if you accept that you can do correlative catalysis instead of one more point that I want to make is that even though the catalyst in the final state is correlated, because the marginal is exactly the same, it retains this quality of catalysis that you can reuse it again, right? It's just that you have to use it on an independent system. So you have another copy of row. You can use it with this part of the catalyst, right? And because the marginal is stopped, it's all good. You can use it again and again and again. It's just that in the final state, they're all going to be correlated. Right. So if you accept this definition of correlative catalysis, there's actually a really nice and simple connection with asymptotics. But Alex and other people in the group, 2001 showed that two pure states can be converted to, well, two pure bipartite entanglement states can be converted by correlative catalysis if and only if they can be converted asymptotically. Like if you recall their class in the entanglement theory, or if you actually discovered law, you notice that this condition of entanglement entropy is exactly the condition for asymptotic transformations, pure bipartite entanglement states, right? So we know that in this setting, pure bipartite entanglement states, correlative catalysis is exactly equivalent to asymptotics. Super nice. And this is like one example that we know in entanglement theory that there is this kind of a catalytic asymptotic equivalence. One more remark I want to make, that's an equivalence. One more remark I want to make is that this construction with one, you can actually extend this construction cleverly. I think Ronaldo is one of the people that noticed this first. You can extend this to mixed states too, to show that if you can do something asymptotically, you can also do it that way. So let's come to our question. How powerful is catalysis? The literature says it is at least as powerful as asymptotics because you can do this one-state construction, right? In some settings, we know that it is exactly as powerful. For example, this pure bipartite states, but in general, we don't know. In other resource theory, there are other resource theories where it is exactly equal for all states, Right? I think purity, this is equal, and some other stuff. But for entanglement, seems trickier to show. What we show in this work is that it is exactly as powerful as asymptotics with two asterisks. So let's talk about first asterisk. Call the standard asymptotic set. You have many copies of your state, you do some LOCC, you obtain something, and this something has to be epsilon close to many copies of the final state, right? This is your standard asymptotic. The first asterisk that we have is that we considered a modified version of asymptotics. So instead of requiring the final state to be globally epsilon close to many copies of the final state, we just require that the final state is epsilon close to the final state only on the marginal. This marginal is only on the vector level. So if this is a already complete, this is a bipartite state, bipartite. Here it's also bipartite. It's not the marginal that's only on the state of A or state of B. It's really like on single copy level, it's close to the final state. Our first asterisk is that we show its equivalent. Well, yeah, we consider this kind of asymptotic setting, which might or might not be different. But we know that, or we can show that for bipartite pure states, these two settings are actually equivalent. So you can do the transformation asymptotically in the standard setting, if and only and yeah. So, all right, you study new asymptotics. The standard asymptotics has a lot of uses, right? You can do a lot of stuff with it. Does this marginal asymptotic thing have any meaning? Does it apply in some scenarios? And we would argue yes, because for example, some tasks, some scenarios, some tasks that you want to do, you don't really care that if you have to have many copies of the same state, right? For example, if you want to use the entanglement here to teleport some stuff, you just care that this thing that you have, it's epsilon close to a Bell state, right? And so having something, it doesn't really matter that this thing is correlated to a bunch of other stuff or not. It's just that you care that this thing is epsilon close. So one setting that we think this kind of marginal asymptotic makes more sense instead of standard asymptotics is that suppose you have many copies of the thing, you have a provider that wants to transform, well, you have many copies of the noisy internal states, right? You have a provider that wants to distill this into a certain number of states. Well, you don't maximize it, but the output should be pure. And then in the output, it's going to be used by independent users. Now, because they're independent, it doesn't really matter that these states, it doesn't matter, these correlations here doesn't really matter, right? Because all they see is just the model here. It's just what is the number in this copy. So if you think of it in this setting, marginal asymptotics actually makes more sense because you can maximize how many users you can get by per copy of the input. That kind of stuff. Right, that's it. Yes, now we have the result. So our first result is that we show, okay, this is the second asterisk, is that we show it when the initial state is distillable, then plural to catalysis is equivalent for with marginal asymptotics. So it's sketch of the proof is that the marginal asymptotics to catalysis direction, we actually use the one construction again because all one construction works with usual asymptotics, standard asymptotics. But if you look at it, you look at it carefully, turns out that it also works with marginal asymptotics. So this direction is kind of like, okay, it's easy, right? The harder direction is the other way around. But, well, turns out if you know where to put the assumptions, it's not super hard either, because you notice if the initial state is distillable, you can actually create the catalyst from a fixed number of initial states. Because it's asymptotic, it doesn't matter, right, that you use a constant number of copies. You're looking only at rates. So in this way, we have both ways, and yeah, we have the theory that for distillable states, well, for initial distillable states, for the process is equivalent to marginal asymptotics. You might look at this and be unhappy because, okay, sure, but you're doing things for mixed states and bound are difficult, but you're assuming distillability, so it's getting around the problem, right? It's getting around the hardness. But one thing I would say to that is that, well, it shows that, or at least some settings, right? Two cubic states. This is a general equivalence, right? Because there are no bounded time states. So you can transform one state into one 2 cubic state to another 2 cubic state by project catalysis, if and only if you can also do it in this marginal asymptotic setting. And second remark I want to make is that this also works in multipartite setting. It kind of almost all the pictures, well, the first picture I only had 2 parties, but you can actually consider multipartite entanglement kind of theory, right? You have multiple parties, you go OCC and stuff. This theorem still holds in this setting. The only catch is that you have to figure out what does this word distillable mean. In multipartite setting, one way we can make it work is that distillable means any pair of parties can distill a bell pair. That's saying that if you can do this, then we also have our theorem. It's good. All right. So now the second result that we have is about distillable entanglement. But in your bank, how do you get more entanglement from your thing? So standard distillable entanglement is defined this way, right? Now, having a bank means you can do catalytic transformations instead of just LCC. So you can define a catalytically distillable entanglement or something by just changing this lambda instead of LCC. You can do catalysis here. You can define a rate, and you can ask yourself, is this rate bigger than the standard non-catalytic distillable entanglement? In general, it is, because catalysis is more powerful in general, right? But the surprising thing that we showed is that it cannot increase if you allow product catalysis. So even under this more general set of operations, you cannot increase the distillable entanglement any distillable state. And this is surprising because you think that catalysis can do more than this general stuff, right? But turns out no. And sketch of how we show this is we basically use the previous result. Turns out it's powerful enough to do this. So 3 steps. One step, you notice that standard rate of the stable entanglement is less than marginal rate because marginal asymptotics is broader, it has less restrictions than standard asymptotics. And turns out in marginal asymptotic setting, marginal rate and marginal catalytic rate is actually the same. That is first step. Second step, you do the same chain, but going through catalytic rate instead of marginal rate. Standard rate is less than catalytic rate, of course, which is less than marginal catalytic rate. Because again, standard asymptotics more restricted than marginal asymptotics. And in the last bit, we show that this marginal rate is actually equal to standard rate. So all the rates here are actually equal. Well, okay, we showed this if the target state is a pure bipartite state. So once you have this, all these rates are actually equal, right? And in particular, the standard rate of distillable entanglement is equal to catalytically distillable entanglement. And therefore, we are Right, one catch is that we showed this marginal catalytic, equivalent, no, catalytic asymptotic equivalence is for distillable states, right? So this reasoning then holds only for a distillable state. But I mean, this is a theorem, right? If you start with the distillable state, you cannot increase the derivative clauses, so everything is good. One question you might ask now is that what happens if you have a bottom entitled state? So in a separate paper, but appeared on my web correctly from Sydney, Ludovico and Bartosz and Alex also showed that there exist bottom entitled states that cannot be distilled in their catalysis. So catalysis, it seems like from this slide, catalysis doesn't actually help you to distill stuff. Yeah. So to conclude at this point, summary, we showed that catalysis is exactly as powerful as marginal asymptotics for distillable state. We also showed that catalysis cannot increase distillable entanglement. Open questions are, can we show this general equivalence even for bottom entitled states? Because we read with our technique, we kind of not sure how to handle this. So it's really interesting. Okay. Second thing is whether the gap between the new setting of marginal asymptotics and standard asymptotics. So yeah. And with that,
Okay, thanks for the talk. Any questions? Yeah, okay. I was wondering, like, so everyone's using this dual state, and I was wondering how good is it when you, let's say, have the restriction on the dimension? Do you, well, it's like not very related to your talk maybe, but do you have any teaching if you restrict the dimension of the catalyst, for example, for these kind of tasks? Is dual state like really the best thing you can use? Or
so I think it's out of battery. I can just speak real loud. So one thing that we the general equivalence shows, in general, if you don't have any restriction on dimension, considering one state is enough in some sense, because if there is a catalyst, there's also a catalyst in one form that will do the job. If you add the dimension in, like the dimension restriction of catalyst, then short answer is I have no idea.
I have a couple of comments. So one is, I really like, all of these words within one construction by all means use it, but I take strong exception to considering this a single shot catalysis construction, because it seems like the catalyst for one problem instance and for another problem instance are so, but they are different in a very asymptotic limit kind of sense, and they're Frankian. So to me, these are very interesting and important results. And in particular, when you show no-go results using that one construction, that's really strong. If you're saying even if you use this construction as your catalyst, for example, it can't increase distillable entanglement, that those are really nice results. But yeah, I would question the interpretation of this as a single shot catalysis.
Well, I would reply that it's single shot because you only need one copy of the actual state, right? Yes, the catalyst actually writes many copies in different state, but this is a catalyst, right? So you can reuse it indefinite number of times. And
The
it's
same properties.
for,
So-
for the same transformation.
I mean, I don't mean to like solve this debate here.
I understand,
Just
I understand.
going through the system. The other thing is, again, with the marginal, this
Marginal asymptotic.
claim that, people make where they say they're independent users. I don't think you're thinking that through because like the implications there are like those independent users would have to never talk to each other ever again. It's like they live in separate universes after that. Because essentially, if not, you're assuming that the map that takes some multipartite state to a direct product of the marginals is allowed. Like a channel or something. It's not.
I didn't take that next talk.
Reference this debate, maybe the reason I gave the sermon yesterday was a bit because of this debate, where if you instead don't think of it as catalysis, but think of it as an entanglement battery, then you don't have this problem. You still get the single copy usage. You still get the entropy difference as being the amount of entanglement that is used up somehow in this entanglement battery or catalyst, whatever you want to call it. So I think that enables you to think about it, which doesn't have the same conceptual difficulties as thinking of it like a kind of a single category user for targeting two.
I was interested in if you have investigated the resource that is spent on correlating to the catalyst. And like probably at the expense of this thing.
Resource in what? Like what kind of resource do you need to correlate the system catalyst?
Yeah, what resource?
Experience no. Because it's, yeah, like that is created as a resource to yourself, right? You can do any OCC for free, and within that it's, yeah.
Maybe we can move the discussion to the coffee or to the lunch break and continue with the next.
Thank you.